Welcome to AI Paper Slop. We are jumping right in today. The paper is Dense Supervision, Sparse Updates, on the sparsity and geometry of on-policy distillation. This is from Guo Yu and the teams at Nanjing University and Alibaba Group.
Yeah, and look, if you are building post-training pipelines, you really need to hear this one.
You absolutely do. The core insight here is, well, it's about on-policy distillation, or OPD.
Right.
That's where your student model generates its own training data, but you have a teacher model giving it this dense token-by-token feedback.
Exactly. And the huge surprise is what happens to the weights. You would think dense feedback means a massive rewrite of the model.
Right, like standard fine-tuning.
Exactly. But the updates are actually incredibly small. I mean, they're coordinate-sparse, they're mathematically concentrated, and strangely, they actively write away from the dominant pathways of the neural network.
Which is just wild. It's this fascinating contradiction, right?
It really is. The learning signal you feed the model is massive and dense, but the structural changes to the weights look almost exactly like those sparse, isolated edits we usually see in reinforcement learning.
It just buries the new reasoning capabilities in these low magnitude coordinates.
Completely ignores the principal directions.
So for the listener, this means if you are selecting optimizers for your pipeline, like deciding between AdamW and SGD.
Or if you're relying on standard LoRA to capture these task vectors.
Yeah, exactly. You might be fundamentally crippling your model's performance without even realizing it.
Totally. To really get why this paper challenges so many of our assumptions, we kind of have to map out the post-training landscape first.
Right. Figure out where OPD actually sits.
Yeah, exactly. You have to see where it sits relative to supervised fine-tuning or SFT and reinforcement learning. So let's start with standard SFT and offline sequence-level knowledge distillation.
Okay, lay it out for us.
So in those traditional offline regimes, you're dealing with a fixed data set. You have dense token-level labels. Every single token in the sequence gives the model a gradient to learn from.
A massive amount of information.
Right. But the fundamental flaw is that the model is being forced to fit external pre-recorded trajectories. You're training the model on sequences it would literally never naturally generate on its own.
And that leads directly to the classic distribution shift problem. Like if you are predicting tokens based on a fixed trajectory, the very second your model makes a tiny mistake during inference,
it
finds itself in this alien latent space.
Yeah.
The next token it predicts is conditioned on a mistake that wasn't anywhere in the training data, and the errors just compound and destroy the output.
Exactly.
It's like learning to ride a bike by exclusively reading a fixed textbook.
Oh, that's a great way to put it.
Right. You are getting all this dense information, but it's completely disconnected from the actual physical act of balancing.
Yeah, which frames the transition to the other side of the spectrum perfectly. Over on the other side, you have reinforcement learning with verifiable rewards, or RLVR. Think of methods like GRPO.
Where the model is doing its own thing.
Exactly. Here, you finally move to on-policy data. The model generates its own samples, explores its own latent space, so that distribution shift is basically eliminated.
Which sounds great, but there's a catch, right?
A huge catch. The trade-off is the learning signal. You lose that dense token-by-token guidance. Instead, you just get a trajectory-level reward.
So the model generates, like, a massive 2,000 token chain of thought.
Right. And a verifier at the very end just gives it a simple 1 or 0, pass or fail.
Okay, so sticking with the bike analogy,
Right.
RLVR is like actually getting on the bike, pedaling for a mile, falling over into a ditch, and just getting a fail grade at the end.
Yeah, pretty much.
You have absolutely no idea which specific movement caused the crash. Was it a bad pedal stroke? Did you lean to the left? You just don't know.
And that right there is the massive credit assignment problem. You have on-policy data, sure, but the feedback is sparse and incredibly noisy.
Which brings us to the sweet spot, the exact center of this landscape.
Yes, on-policy distillation, OPD. It solves the credit assignment problem of RLVR and the distribution shift problem of SFT.
Best of both worlds.
Exactly. The student model still samples from its current policy, generating its own physical rollouts, but instead of a pass-fail grade at the end, you bring in a highly capable teacher model.
Oh, okay.
And that teacher evaluates the student's rollout and provides dense, token-level feedback, usually through KL divergence, on every single step.
So back on the bike. You're feeling the balance natively, but now you have an expert coach sprinting alongside you.
I love that, yes.
And the coach is instantly correcting your posture, your grip, every single second.
Yep.
It's dense feedback applied directly to your own physical rollout.
It's the ideal learning environment. But historically, the assumption in machine learning has been that the density of the learning signal dictates the density of the weight update.
Right, like dense signal equals massive changes.
Yeah. If you use dense SFT labels, the gradients touch everything, and you get a massive, dense rewrite of the network parameters. If you use sparse RL rewards, the gradients are noisy and directional, so you get sparse parameter updates.
But this paper completely dismantles that assumption.
Completely.
Yeah.
And that brings us to what we can call the sparsity paradox.
The sparsity paradox. I like the sound of that.
So you have that coach screaming dense KL divergence feedback on every single token the student generates. But when the authors actually measured the resulting weight matrices...
Across models like ds-Quen, mini-CPM, and Quen 2.5 VL, right?
Yeah, exactly those. They found the network barely touched its parameters.
Wait, really? Barely touched them?
Barely touched them. They measured this using the relative Frobenius norm, which basically calculates the total geometric magnitude of the update matrix relative to the original weights.
Okay, and what were the numbers?
For the OPD runs, the relative global norm is microscopic. It's between 0.036% and 0.142%. Yeah, the model is practically identical from a distance. And when you look at coordinate sparsity, setting a tight threshold of 1E5 to filter out background noise, between 66% and 89% of the coordinates show zero visible movement.
That is insane. For contrast, the authors ran an offline sequence-level distillation on Quen Math Distill, right?
Right, an offline run.
And in that offline run, the relative norm was 11.9%. The sparsity was only 3%.
The offline process violently overloaded the network.
But OPD, despite having dense token-level feedback just like the offline run, kept the updates incredibly sparse.
Exactly. And the updates that did happen were highly localized. The largest relative movements almost always appeared in the feed-forward network modules, the FFNs, rather than the attention mechanisms.
Which, I mean, if you think about it, making changes in the FFN modules makes architectural sense.
Totally. Attention layers route the information, right? They determine where to look in the context window. But the FFN layers act as the associative memory.
They map specific features to higher-level concepts.
Yeah. So if the model is refining a specific reasoning capability, it doesn't need to change how it reads the prompt. It just needs to adjust the specific logic gates in its memory.
Okay, wait, I'm stuck here. I'm going to push back on behalf of the listeners.
Go for it.
Let's look at this purely mechanically. If the teacher model is providing a dense KL divergence penalty on every single token, forcing the student's probability distribution to match the teacher's.
Right.
You are generating massive gradients across the entire sequence. So where does that dense mathematical signal go, if not into a massive dense weight update? Why doesn't it just rewrite the brain?
It's a great question, and the answer lies entirely in the familiarity of the data distribution.
Familiarity.
Because the student is generating the sequence on policy, the rollout exists in a highly familiar, comfortable region of its own latent space.
It already knows the neighborhood.
Exactly. The model already knows how to generate these tokens. The dense feature signal isn't forcing the model to learn completely foreign concepts from scratch.
It's just tweaking it.
Right. It's simply asking the model to slightly amplify or dampen probabilities within a structure it already natively possesses. You don't need a dense parameter rewrite to make a microscopic course correction to a behavior you already own.
That completely reframes the entire process. You aren't building a new circuit. You are literally just fine-tuning a few specific switches.
And what makes this even more compelling is what those specific switches represent.
Oh, the mask overlap, right?
Yes. The authors took the sparse mask of coordinates updated by ds-Quen during OPD, and they overlaid it with the coordinates updated by Deepscaler during an RLVR run.
And they found a match.
A striking match. The coordinates altered by the dense OPD process and the sparse RLVR process intersect at a rate roughly 3 times higher than random chance.
3 times higher. Wow.
They are both independently discovering and modifying the exact same reasoning subcircuits within the FFN layers.
Okay, but if I'm an ML engineer listening to this, I hear the phrase sparse mask, and my immediate reaction is, well, skepticism.
Sure, neural networks are noisy.
Exactly. Is this sparsity just a statistical artifact? Is it just a byproduct of how we measure the checkpoints? Or is this tiny fraction of altered coordinates actually doing the heavy lifting?
It's a valid concern, because if it's just background noise, we shouldn't be optimizing around it.
Right.
But the authors anticipated that exact skepticism, which is why they ran interventional reality checks.
They didn't just passively measure it.
No, they physically tested them, they took the source model, initiated the OPD training again, but they applied a hard freeze to every single parameter outside of that discovered sparse mask.
Oh, wow. So they mathematically forced the model to only route its learning through that tiny fraction of active coordinates.
Exactly. And the performance recovery is the definitive proof here.
Let's talk about the numbers on that, because they use the A math reasoning benchmarks, right? Which are incredibly rigorous.
Extremely rigorous. So the full unconstrained OPD run achieved an accuracy of 35.52%.
And the interventional run, the one restricted entirely to just the tiny sparse mask.
It hit 35.10%.
That is wild. They practically recovered the full training performance while blocking updates to, what, like 80% of the network?
Yeah, exactly. And furthermore, they ran a control where they used a random mask with the exact same sparsity density.
Let me guess. Performance tanked.
Plummeted. Completely failed. This proves that the specific sparse coordinates discovered by OPD are not a statistical artifact. They are functionally critical.
The delta produced by OPD acts as a highly specific operational sparse task vector.
Exactly. And this operational reality leads directly into a massive debate currently happening in the post-training community regarding optimizer selection.
Oh, the AdamW versus SGD debate.
Yes. For standard SFT, everyone defaults to AdamW, but it requires massive memory overhead because you have to store the first and second moments.
The momentum and the variance.
Right, for every single parameter. But recently, several papers have shown that for sparse RLVR updates, vanilla SGD is actually highly competitive.
So you can drop AdamW, save a ton of memory, and get the same result.
For RLVR, yes.
So here's my question. If OPD results in a sparse task vector that looks basically identical to RLVR, why does this paper explicitly warn against dropping AdamW for OPD pipelines?
It is a brilliant patch by the authors, and it really highlights the danger of confusing the final destination with the journey.
The journey. Okay, unpack that.
The final weight update in OPD is sparse, yes. But the training dynamics required to reach that sparse destination are vastly different from RLVR.
They ran a direct ablation, didn't they? AdamW versus SGD in the OPD setting.
They did, and
Yeah.
SGD maxed out at 37.9% accuracy. AdamW pulled significantly ahead to 42.4%. SGD demonstrably fails to capture the full reasoning capability.
Let's break down the mechanism there.
Yeah.
If the final update is just tweaking a few isolated coordinates, why do we need the complex coordinate-wise adaptive scaling that AdamW provides?
Well, what is AdamW actually doing during the training step that SGD cannot handle?
Right.
AdamW tracks the second moment of the gradients, which is essentially the variance or the shifting scale of the updates over time. In RLVR, the reward is sparse and trajectory level, resulting in gradients that are generally more uniform in their directional push.
But in OPD,
But in OPD, you have that dense teacher signal applying supervision on every single token of an on-policy rollout. Because the student is exploring its own space, it might generate a highly unexpected token.
prompting the teacher to freak out and apply a massive localized gradient correction.
Exactly. And then on the very next token, the student might behave perfectly, resulting in zero gradient.
Oh, I see. So you have this incredibly chaotic gradient landscape. The scale of the corrections is swinging wildly from token to token and from coordinate to coordinate.
Precisely because the teacher is micromanaging an erratic student.
That makes perfect sense.
The authors analyzed AdamW's internal states during the run and found that the second moment coefficient of variation remains exceptionally large. It averages around 4.85.
4.85. That indicates massive gradient heterogeneity.
Massive. AdamW is constantly normalizing these wild swings, ensuring that the learning rate is appropriately scaled for each specific parameter.
And SGD just takes the raw, chaotic gradients at face value.
Right, which prevents the model from efficiently navigating to that optimal sparse configuration. The dense teacher signal demands an adaptive optimizer, even if the final result is sparse.
So for anyone building these pipelines, the takeaway is clear. Do not swap out AdamW for SGD in your OPD setups just because it works for RLVR. You need that adaptive scaling to handle the dense token-level feedback.
Absolutely. Do not drop AdamW.
Okay, let's shift gears to the final major session of this paper, moving from the coordinate space to the underlying geometry of these updates.
The geometry is where things get really weird.
We know they are sparse, but how are they mathematically structured?
We have to look at the spectral concentration of the update matrices. When you run a singular value decomposition on these 2D weight updates, you find that they are numerically full rank.
Huh?
If you set a microscopic threshold, essentially all the singular values are non-zero. The update is technically touching all dimensions.
But the distribution of the energy within those dimensions is highly skewed.
Highly skewed. The energy is incredibly concentrated. The top 16 singular values hold between 20% and 40% of the entire update energy.
That's a huge chunk.
Yeah, and if you look at the median stable rank, which measures the effective dimensionality of the matrix, it sits remarkably low, usually between 7 and 20.
Okay, so it is technically full rank, but the vast majority of the meaningful change is concentrated in just a few mathematical dimensions.
Right.
But the truly counterintuitive finding is where those dimensions are actually pointed. The geometry is actively off principle.
Yes. And this is the defining geometric signature of on-policy learning.
Explain that for us.
During pre-training and standard SFT, a neural network develops principal singular directions. You can think of these as the dominant highways of the weight matrix.
Well, highways, got it.
They hold the highest magnitude weights and govern the core representations of the model. You would naturally assume that when a model learns a new, highly complex reasoning task, it would leverage and amplify those massive highways.
But OPD does the exact opposite.
The exact opposite. The joint principal projection, which measures how much of the new update aligns with those dominant source directions, is practically zero.
Zero.
Basically.
Yeah.
At a 10% rank fraction, it sits below 1%. The model explicitly avoids writing to its main highways.
That is fascinating.
Instead, the authors note that up to 48% of the visible updates fall directly on the bottom 10% of the source coordinates.
So the model is actively seeking out the dormant, low-magnitude parameters.
The backroads of the neural network.
The backroads. And it's etching the new reasoning task vector into those isolated spaces.
It is an incredibly elegant mechanism, if you think about it. By writing to the low-magnitude coordinates, the model preserves the core representations it built during pre-training.
It doesn't destroy its foundational knowledge to learn how to solve a specific math problem.
Exactly. It just activates previously underutilized capacity.
Okay, let's tie this directly to parameter-efficient fine-tuning.
Let's do it.
Because if you hear that an update is spectrally concentrated, that all the energy is in a stable rank of 7 to 20, your very first instinct as an engineer is to use LoRA.
Naturally.
Low-rank adaptation forces the update into a low-rank bottleneck, which sounds absolutely perfect for this geometry. But if the update is also technically full rank and explicitly off principle, doesn't that mean standard LoRA is going to fundamentally fail to capture the actual task vector?
It creates a severe mathematical tension.
Right.
LoRA is computationally efficient precisely because it isolates a few dimensions. And because the OPD update energy is concentrated, LoRA will successfully capture the broad strokes of the update. But standard LoRA matrices, based on how they are initialized and optimized, possess a strong inductive bias toward the principal components of the pre-trained weights.
They naturally want to align with the highways.
Yes. They are magnetically drawn to the highways.
But the OPD update isn't on the highways. It is deliberately hiding in the low-magnitude backroads.
Which means a low-rank adapter will struggle to accurately reproduce these delicate orthogonal edits without accidentally overriding the principal directions.
Wow.
LoRA forces a global low-rank structure that lacks the localized precision to flip specific, isolated, low-magnitude switches.
So if standard LoRA is basically leaving performance on the table by missing the off-principle edits, where should the community be looking? What's the alternative?
The geometry points directly toward exploring orthogonal fine-tuning methods.
Okay, like what?
Techniques like OFT or BOFT, that's butterfly orthogonal fine-tuning.
Okay, and how do they differ from LoRA?
These methods operate differently. Instead of forcing a low-rank additive matrix, they apply orthogonal transformations that preserve the hyperspherical energy of the pre-trained model while allowing for highly expressive rotations.
Oh, I see.
They are much better suited mathematically to capture these off-principle backroad updates without disturbing the dominant highways.
That is a massive architectural takeaway. If you are using on-policy distillation to extract reasoning capabilities from a frontier model, relying on standard LoRA might be blinding your student model to the actual sparse task vector it is trying to learn.
You have to align your PFT strategy with the actual geometry of the update.
This entire paper is just a masterclass in reevaluating baseline assumptions about post-training mechanics.
It really is.
Let's pull all of this together for the listener. The footprint of OPD is entirely unique.
Very unique.
Because it uses on-policy data, it generates sparse, highly localized edits, acting essentially as a surgical task vector, primarily within the FFN layers.
Right.
And because it uses dense teacher feedback, those gradients are highly chaotic, meaning you absolutely must retain the adaptive scaling of AdamW.
Do not drop it.
And geometrically, the updates are spectrally concentrated, but actively off-principle. They heavily favor the low-magnitude backroads, which directly challenges the default use of LoRA and demands a serious look at orthogonal methods.
It sits perfectly between the offline brute force of SFT and the sparse noise of RLVR, proving that dense supervision does not require dense parameter destruction.
Which leaves us with a lingering theoretical question, something that fundamentally shifts how we view model optimization.
Oh, I know where you're going with this.
For years, the conventional wisdom in AI alignment was that the density of the reward dictated the shape of the update.
We just assumed dense SFT labels caused dense rewrites and sparse RL rewards caused sparse edits.
Exactly. But this paper isolates the variables and proves the reward density is merely a secondary factor.
A byproduct, almost.
Right. By keeping the dense token level signal, but moving to on-policy data, the updates instantly became sparse.
It proves that the data distribution, whether the model is comfortably exploring its own familiar rollouts or being violently forced to fit fixed offline traces, is the true architect of the neural network's geometry.
The familiarity of the latent space is what protects the network from massive parameter rewrites.
Which raises an incredible point about latent capacity.
I mean, just think about the implications for the next generation of self-improving reasoning models.
Right.
If on-policy data naturally isolates learning updates strictly to these sparse, underutilized, low-magnitude backroads without overriding the core pre-trained highways, how much untapped capacity is still hiding inside these models?
It's a huge unknown. How many specific reasoning subcircuits are just sitting dormant, waiting for the right on-policy coach to provide the dense supervision needed to unlock them?
We might be vastly underestimating how much these networks can learn before they actually run out of room.
Discovering how to efficiently map and utilize those off-principle backroads will undoubtedly drive the next major wave of post-training research.
There's no question about it. This paper completely changes the map. Well, thanks for joining us for this look at AI paper slop. Keep building, and we will catch you next time.